what we have done in the last class is we have some parameters and we had a differential equation. So the differential equation was this. What was the differential equation? So the differential equation was this 2.9 was the differential equation. The rate of change of concentration is equals to F upon V. Initial concentration minus F upon V. The concentration at any time point. What was F? So if you remember, let me go back. So F was the flow rate, C was the concentration, and V was the volume. And we assume that the flow rate was constant. We further assume that the volume was constant and concentration was changing. And the differential equation, if you can see, I think I will make it a bit bigger. The differential equation you would see in equation 2.9 is showing the rate of change of concentration in the tank. And so this F upon V, since F is constant and Vf is constant, so if we divide both of them, we will get some constant number. So this can be, you can always think of it as 3 upon 5 or 7 upon 10 or something, but the result would be a number at the end. So it's a constant. So don't no need to worry about that. So if something is a constant, I don't bet an eye on that while solving differential equation. So this is C naught. This is actually initial concentration, which is also constant in certain cases, in most of the cases. So the only thing which is actually variable in this equation is the C, concentration at any time t. And this C is dependent variable. The concentration is dependent variable. Of course, the water is coming or a liquid is coming to a tank at a certain flow rate with a fixed volume. Then the concentration in the tank would change after some time. That would be a function of time. So it's a dynamic variable where it is changing with respect to time. So dc divided by dt is a function of a constant minus a function of c. So f upon v in this case is a number. C naught would be an initial number. If you can look at the example, I think you have been given some numbers. It's over there. So you can see that you have been given value of f naught, your f, you have been given value of v, you have been given value of c naught, and you have also been given the value of c. So the concentration at any general concentration is 0.925 kilogram per cubic meter, whereas initial concentration was 1.85. So, okay, that was an autonomous differential equation in which the flow is changing with respect to C only. Now, um, the general solution of the differential equation would be something like over here. So, the general solution of differential equation should always give us, the point is if it is dy by dx, we need to remove d by dx just to make it y. So we need to integrate it and then do either integration by parts or either by finding integrating factor or something else. We actually have to solve it to get the solution. Right now, I'm not quite concerned about getting the solution because you would be doing mostly it by using some code. But since you have been to the differential equation course, you should know how to solve a very simple differential equation. So this differential equation would be thought of as dy by dx is equals to a y naught minus by. So that's a very, very simple differential equation, and you should be able to do that. Now the initial conditions was alhamdulillah, alhamdulillah. Okay. Now the initial condition was, I'm sorry, when t was less than equal to zero, the initial concentration was C naught was equals to C in it. But when initial concentration was greater than zero, then this equation would be used because when we didn't start recording the time, there was no flow, there was no nothing, just there was some water or there was some liquid in the tank, and that's all. So the initial concentration at t equal to zero is equal to C I N I T. Now, when we replace to find the value of unknown constant of the differential equation, because the solution is actually over here, what the solution is saying that it's dependent upon the initial concentration plus some rate times the decline function, exponential decline function. So the negative sign says that it's an exponential decline function. So I can give you a really quick plot for that function if you're interested in. Sorry. Okay, so that was some another example I was working at, and you can see that it's an exponential function. So the equation over here is n naught times exponential of alpha t. So that was actually the equation. So what was the equation? Equation is n of t is equals to n naught into e to the power alpha t. So if you look at it, it's something like that. So the only difference is it's n of t. So it's written c of t is equals to n naught. It's written c naught, and it's being added, and that part is being actually being multiplied. So there is no k, there is no e, and then there is so c of t is equals to c naught plus ke minus f upon v times of t. Once again, f upon v would be a number, so that would be minus 0.5 t or something, or minus 0.7 t depending upon the values of f and t. So that's actually an exponential function which is being declined. So the concentration would always be declined. Why? Because of the exponential term. There is a negative sign in the exponential term. So we looked at a very simple system. I think I need to make it a bit bigger so that you can see the equation. Let me give a second. So actually that was the equation. So it's n naught. So n of t, I am calculating n at any point t. Similarly, as I was calculating concentration at any point t in the example in the book. So it is n naught times exponential e to the power b. What is b? It's k over there. So b times of t. So that's actually the solution. Uh, so the only difference is k was outside over there. So sorry, it was not k. It's f upon v. So b, the value of 0.02 in this case is actually what's minus not minus f upon v into t is doing. So it's because it's inside the exponential. Now, if you look at it, initially the value is the same, and then when the time starts changing, you can see the value starts increasing. So we started with 3 million or something, 3 billion, I think. And then we are going to 3.3, 3.7, 3.8, 3.9 as the time passes. So what would happen if I put a negative sign into exponential? So what I was saying that it's an exponential decline function. Why there is a negative sign? If there was not a negative sign, it would be an exponential increasing function. So you can always look at the plot and then give it a try. So in this particular case, let me draw it a bit neatly. So if you look at it, you can see that it's actually going up, and t is the time which is over here on the x-axis. Okay, that was badly drawn. Forget the time. But if you can see that actually it shows an exponential increase. So we start at 3 into 10 to the power 9, and after some time we are almost getting at 10 into 10 to the power 9, or 1 into 10 to the power 10, something like that. But so that's actually exponential increase. So we are increasing exponentially. Let's take a smaller value for that. I don't think. Okay, now another example would be what would happen if I have an exponential decrease or exponential decline. So that's actually exponential increase. And if I copy and paste the same formula, just put a negative sign over here. That's all. This would show me an exponential decline. So if you go through same time length, you can see that it's started to decrease. So if I plot this, you can see the exponential decline. So we started with 3 into 10 to the power 9, and we are almost below 1 into 10 to the power 9 or something. So this is called exponential decline. So when there is a negative sign, there is an exponential decline. When there is a positive sign, there is an exponential increase. Now, let me copy this sheet and put it over here, and let's go give it some sensible value. So if it is 3060, which is more easier to comprehend, I always struggled in big numbers. So when it is 3060 or something, so that's a sensible number to think about. Make it 3000. Now, if it was 3000, you can see that exponential increase for 3000 actually is quite obvious over here. And if I keep on pushing the time, so the time was 60 minutes or 60 seconds or 60 hours, whatever. So if I keep on pushing the time and I keep on pushing the decline and everything, let me do it a bit more. So you can clearly see the exponential trend. I think I've done it right. Okay, so this is the exponential decline. You started with 3000 and you are near about less than 500 in a matter of, I think, 120 days or 134, 135 days. So this is an example of exponential decline. So the curve would always decline. And there is one thing called exponential increase. So you started with 33,000 and you are sitting on around 45,000 and something at this time point at 136 seconds or minutes. So this is an example of exponential decline and this an exponential increase. I'm deliberately not plotting them on a single sheet. Otherwise, the scale factor would introduce a large discrepancy. I mean, you can see that. So exponential decline is not evident because of the scale factor for exponential increase, but it's still going down. You can see that for series number one is exponential increase, series number two is exponential decline. Okay, so that's all for the exponential function or exponential curves. Um, if you go back to the solution, and so my point was concentration at any time point t would be initial concentration, then the difference between the initial concentration at any time point at C naught, and it would be then multiplied by minus f upon v. So the graph would always go downwards. So that's an exponential decline. So that was my point I was trying to make. So you can see that. uh, Come on, it's not exponential decline, it's exponential increasing. Interesting. Okay, so it will increase in the beginning. It shows an increase in the beginning in the concentration, but the concentration which is being added will always be reach a threshold, and then it will start to it will stop. So okay, so that was not an exponential decline. The reason is it is not being and I can see the reason. The point is it is not being multiplied rather than it is being added. So it will become a logistic curve. Did I talk about logistic curve in the last class? So a logistic curve is an exponentially increasing curve that will increase exponentially, and then that would stop at a certain time point. Say for example, if you have bacteria in a petri dish, and then you keep on growing the bacteria. So they would grow very, very quickly in the beginning. At the very end, the number of bacteria in that dish would be equal to the maximum number of bacteria in that dish, would be the number of bacteria that dish actually can hold. You cannot have a number of bacteria in a room, and you that can occupy a room, and you cannot put them in the petri dish. So the maximum number of the population would be equal to the area of the petri dish. So this is called the carrying capacity. So an object cannot rise beyond the carrying capacity. So that's actually the difference between exponential and logistic function. It's not logarithmic, it should be logistic. So if you look at the video between exponential and logistic, oh sorry, the images. So this shows it what actually I'm saying. So the exponential function will keep on increasing, and it could be thought as an uncontrolled growth. However, the logistic function will will stop at the carrying capacity. So the population cannot increase more than some 82 or 85, a number something like that. Whereas exponential function shows an uncontrolled growth. This is again the difference between exponential and logistic. So there are quite good examples in. I was looking for a particular. So this is actually once again population growth and logistic function. So this shows exponential growth where rate of change is equals directly proportional to the population, and this shows the logistic growth where k over here represents the carrying capacity. So a system cannot sustain more than that population, otherwise they will start to die. This is world population, I think, predicted. So the carrying capacity of world is assumed to be 100 billion. We cannot have more than 100 billion people. So if the exponential function continues to increase, we will have, if exponential pattern is being followed, which is not being followed, we can have more than, so in 2800, we will reach the carrying capacity of the world, somewhere about that. We will actually, even before that, we would surpass the carrying capacity of the world. Whereas if the population follow a logistic growth curve, we will survive a bit more. These are just some assumptions. So these are the differences. So this type of curve, what I was talking is, in this example, it's a logistic curve. So if I run it, oh, come on. So if I run it, you can see. So the population initially starts increasing, and after some time, it went towards the carrying capacity of the tank. So that carrying capacity is around 1.8 or something, not more than that. What's the point at the end? So the carrying capacity of the tank is 1.834. As I can see it, it's a very small number, but it's 1.834. And if I integrate it for a larger bit of time, you can see that it will stop over there. No, I won't save it. So you can see that it's not passing that particular point. So it's 1.85 is the maximum you can go. Let me zoom it a bit for you, all of the section. So you can see that this is the carrying capacity of the system. So the system cannot expand beyond that point. So after that, what would happen is that the system becomes time invariant. No matter how much time is being passed, or how many minutes, hours have been passed, or seconds have been passed, system has no effect at all. So after reaching beyond carrying capacity, the value of y-axis doesn't change at all. So this could be thought of as an example of a logistic curve, a special logistic curve. Next is modeling of a mechanical system. So that was a flow diagram, and that's actually of a mechanical system. Um, More towards your mechanics courses. Anyway, so this is actually the dynamic response of the tank, um, or the flow rate we just studied. So the models of mechanical system are important in control engineering because a mechanical system may be a vehicle, a robot arm, a missile, or any other system which incorporates a mechanical component. Mechanical systems can be divided into two categories: translational systems and rotational systems. We are only looking at translation ones. Now, there are three components mainly. The basic building blocks of translation mechanical systems are mass, spring, and dashboard. So there are three parts for, and they are shown at equation number, figure number 2.9. So it shows the springs only, spring under certain conditions. Now, the input to the translation mechanical system may be a force, and output would be the displacement. So mostly we are looking at the output and input, and what is actually working in response to that input in order to get you a proper output is actually a spring, a mass, and a dashboard. So that's actually would constitute a translational mechanical system. So we will look at each component separately. So first thing is spring. Whenever you have a concept of spring, always remember Hooke's law. Force is directly proportional to the extension in the spring. So spring store energy as shown in figure 2.9 and are used in most mechanical system as delay elements. So they can cause delay of the response because they store energy for some milliseconds. Um, As shown in figure 2.10, and some springs are hard, some are soft, and some are linear. So there are certain types of springs. So some are hard, so the harder spring, so the displacement and forces, the more the force is applied, the so it's linear to a certain range between a force and a displacement. But after a certain limit of displacement, or the force, it would start acting non-linear. You can see that the relationship. So the number of displacement is directly proportional to number of force applied. The number of displacement is directly proportional to the number of force applied. Over here it's inversely proportional. But when you go beyond a certain limit, so the amount of displacement starts not getting proportional to the force applied. So they are getting a bit lesser. This line should continue on that path rather than it started to curve upwards. So what it means is the more the force applied, the displacement is not changing uh, with respect to that proportion, or the more the displacement, the we require the uh, lesser the force, but after a certain point. So if force reaches a certain threshold, after that the linear system would break. Similarly, if you go to the soft spring, same thing, the linear force system would continue to obey. But after some time, if you pass a certain force threshold, गड्ढे में गाड़ी डाल दिया आपने बिल्कुल, just put it into the trench or somewhere. So then in that case, if you have soft spring in your cars, it will start to actually bend. So the more the displacement, there would be a lot more displacement with lesser amount of force applied. Similarly, third is just a linear spring. It just translates as it is, the energy as it is, but the only difference is it would introduce a slight delay in that transfer, which is sometimes very important. Now, a hard or soft spring can be linearized for a small deviation from its equilibrium conditions. Of course, it should be within the linear range. Otherwise, the answers, the response would be quite unpredicted. In the analysis in this section, a spring is assumed to be massless or negligible mass. We always assume that there is no mass in the spring. Forces at both ends of the spring are assumed to be equal in magnitude but opposite in direction. The springs in different states, such as compression, tension, and torsion, are shown in figure 2.9a. Oh, we have been to this figure. For a linear spring, the tension is directly proportional to the applied force. So F is equals to Ky. And what is the energy? The energy of the spring, it's half Ky square. It's a very, very famous relationship. This energy is released when the spring contracts back to its original length. So when a spring contracts, the energy is stored in the spring, and then when its spring releases, It releases with the amount of energy, which is 1 upon 2 ky square in this case. If a spring are applied in parallel, the spring constant or stiffness constant would be a mere sum of all the individual spring stiffnesses. If the forces are applied, the springs are applied in series, so it's the same concept as capacitors in series and capacitors in parallel and resistors in series and resistors in parallel. So it's the same concept. Another thing which is important is the dashboard. What is the dashboard? This is actually a damping thing. Sometimes it's a cylinder, sometimes it's a viscous medium, sometimes it will just introduce dampness. So if a spring is compresses, it would relax. And then if this series continues, the let's assume the example of your car's shock absorbers, if they continue to increase and decrease quite rapidly, your journey won't be as pleasant as it is nowadays. So what happens is that immediately spring depresses, so it should release a certain amount of energy. So dashpot actually that damped that release. So immediately the response of the spring is reduced many folds because of a dashboard, because it's usually a cylinder, is usually some hydraulic system, so that actually reduces the response of the spring or the release of an outburst of energy immediately as a response. So that's why we use a dashboard element. So as the piston moves, the liquid passes through the edge of the piston, damping of the movement of the piston. So actually, this damps the movement. The force with the move the piston is proportional to the velocity of the piston movement, and it is given by F is directly proportional to dy by dt. And if we remove the constant of proportionality, it is b times dy by dt. Okay, a dashboard doesn't store energy. A dashboard just destroys the energy. In other words, it just damp it immediately. The effect of that. In this case, the displacement would be reduced. The rate of change of displacement. Now, the third is the mass, which is quite easy to interpret. We are studying it a lot in our physics courses. When a force is applied to a mass, it's F is equals to ma. In terms of displacement, acceleration is a second derivative of displacement. So F is equals to m d square y by dt square, and F is equals to b dy by dt. So in terms of dashport, force is directly proportional to the velocity. In terms of mass, force is directly proportional to the acceleration. Now the energy stored is half mv square, which is very famous relationship, which is the kinetic energy in this case. There are some examples, but we will look at only first, and that's all. Uh, so a figure 2.11 shows a simple mechanical translation system with a mass, with a spring and a dashboard. A force F is applied to the system. Derive a mathematical model of the system. So if you look over here, so this is the diagram. So this is fixed. There is a spring attached to that mass. The force is applied on that direction, and when the spring is compressed and relaxes, the displacement actually would change direction so as the force. Now this C is actually the dashboard over here. This is the dashboard. So the result of immediate spring releasing an outburst of energy is actually being compensated by the use of that dashboard. So it doesn't allow that mass to move rigorously as a result of spring compression. So that's why we use dashboard over here. Now system is quite simple. So the net force on the mass is the applied force minus the force exerted by the spring and the dashboard. So the total force by using Newton's second law. So F was equals to ma. Now there were a couple of forces. So the first force is applied force. You apply it externally. So when the force uses to compress the spring, the first thing, and the force is exerted by a spring as a response. So the response of force the of the force by spring is actually ky. which is the Hooke's law, and the dashport. So the response of the force by, so if you go upwards for a spring, F is equals to Ky. For dashport, F is equals to B dy by dt. For mass, F is equals to md square y by dt square. So F minus Ky minus B dy by dt is equals to md square y by dt square. So F is equals to my, and we are looking at the combined force on the mass. Actually, we are interested in, if you look at the diagram again, what is the combined force on that mass. So there are certain directions. Some of the forces are on right hand side, some of the forces are applied on the left hand side, and so as the signs. So minus ky and minus b, they are being subtracted because these forces are on different direction. And if you compress a spring from upwards to downwards, so the direction is from top to down, so it's from top to bottom. And when the spring compresses, the response is always the inverse. So that's why we put a negative sign for the response. And similarly, the dashport would always behave in the reverse direction to, suppress the output, or suppress, to damp the output immediately. So that's why it's saying that is the applied force, which is F, which is unknown, minus the force exerted by the spring, which is Ky, minus and the dashport. So they both are being subtracted. So this is actually the net force, all or total force. After that, it's just a simple um, algebraic substitution. We take F over here and then we put everything over there. So this is the second order differential equation. It can be solved by using any standard second order differential equation technique. You can solve it by using YC and YP, if you remember, complementary solution and particular solution. And if you can't solve it, there is one more thing, Mustafa ने पढ़ाया, I think, which is Laplace transform. You can always transform this system into a Laplace transform using the Laplace transfer function. So this would be f of s rather than time domain. So this will be in frequency domain. So that would be m s square y of s plus b s of y of s plus k y of s. So y of s upon divided by f of s will become this. So that's actually the block diagram or the transfer function. The block diagram of that transfer function is being represented in figure 2.19. Sorry, in equation 2.19. And the diagrammatic representation is over here. So this is actually what's happening. So this is the force as a function of frequency. This is the displacement, and this is the transfer function. So rather than showing this diagram, this complicated diagram, figure 2.11, then equivalent representative diagram would be this, by using Laplace transformation. And this is you can see that this is the result of step input. So there was a depression immediately of an amplitude of going up to 16, and as a response in the time, you can see that in seconds it's immediately being damped rather than you know falling. So otherwise there would be more fluctuations before going to the damping state. The code is very very simple, just a couple of lines, and it's using a function called step. So if I go to the MATLAB and so if you run it with some initial conditions, okay, yeah, skipped. So it's busy. So these are the step responses of our damping system. So you can see it from the diagram over here. So time is in seconds, amplitude is over here, and you can see that it's being damped quite quickly. So if I change it, say I change the damping parameters or something, so C is actually associated to damping. So if I change it to a bigger number, 5, and then see what happens. So actually I have a lot of programs saved. That's why I'm reluctant to save it. So that's why I just select it and use F9. So you can see that if it is like that, so it's damped immediately. There was no fluctuation at all. If I increase the damping to the damper constant to zero point 0.5 from zero point 0.1, let's see what happens at 0.3, probably, and then F9. You can see that the damping amount still decreases. What would happen if it was zero point 0.1, if I set it to 0.05? I would expect a lot more fluctuation than the original diagram. So this is actually what happens. So the damping function would actually it actually controls the response from the spring as a result of compression. So it stops at the sudden burst of release of energy. So that's why the value they use was zero point 0.1. And if you put it zero point 0.1 again, you will get the same diagram as we uh, see in our book. Same thing. So you can see that it's exactly the same. But if we change the damping, so this is actually where I want every one of you to play. So to see what happens if we change the damping, what would happen if the spring is a bit more stiffer? The constant is right now zero point 0.1. What would happen if a spring is as spring constant of zero point 0.4? What would happen the spring was has a spring constant of 0.001? So immediate you can see that the spring was a bit rigid, so it damped. In fact, the damping was even initially the same, but so if spring is rigid, we need to uh, have more. We need to apply more damping, so we need to constrain it a bit more. So in order in for that, the dashboard system should have more viscous oil or something, or it should have harder brakes to uh, actually immediately damp the response. So we can say a lot if we think about it as a problem, and we can immediately see the result of these um, you know speculations or our simulations when we change these values. So what would happen if mass is changed? The same thing, the mass is 10 times more than the. So you can see that because the mass is a bit more, so the dashboard system was unable to control the fluctuations because mass is a lot. So we need to change the parameter of damping in the dashboard to actually combat with the mass. So when I increase it, immediate thing as expected, it actually reduces the fluctuations. So that's actually these type of observations, and these could we can always think of these type of observations, and I always uh, you know so this is a very very simple code. It's the simplest code you ever seen in MATLAB. So you can always think of the problem by yourself. The problem is not the book, the problem is not the exercise, the problem is not the code. The problem is actually what you understand at the very end. Or in other words, I mean, or if I say it more bluntly, the problem is what you want to understand actually. So you can think of the problem, you can I have given you a basic explanation of that, but you can think of the problem and you need to um, spend a couple of hours on that to think about the changing the parameters. Okay, what would happen if, so for example number 2.1, what would happen if the force changes? What would happen if the volume changes, volume of the tank changes? What would happen if the flow changes? What would happen? So you can always put different values and then see what could be the result of that. So You can always think of it. Now that's all for the second example, and I won't go to example number 2.3. So they are quite hard. Uh, mm, just a couple, and there are some examples from electrical systems which were a bit easier. Mm, these are some of the velocity curves, I think, flight of model rocket or something. Yeah, there are some examples from the electrical systems in which is relatively easier to follow. You know the Ohm's law, you have the RLC circuit, you know the potential energy, the rate, voltage is rate of flow of charge or the potential difference, and energy, they follow the same principle. What was the Kirchhoff's law, voltage law, and current law? And you can, solve the system using MATLAB by using those type of systems, and you can always generate some plots. Probability is a fundamental building block of statistics. If you remember probability, I taught you probability, and probability has two different approaches. First is called frequentist definition, other is called the classical definition. So the classical definition of probability means if we are interested in occurrence of a particular event and we divided it by the total number of occurrences for all events within that sample space, so you will get the probability. But at sometimes you don't have the total number of occurrences or total number of outcomes, or the total number of outcome set is not complete. Say when you are dealing with novel type of situations in which the output can be anything, then you usually don't have a complete set of outcomes. So in that case, we will see that if you repeat an experiment enough times and you are interested in particular output, so out of all of the occurrences or outputs, what is the chance of getting that particular output? And if you repeat it again and then again and then again, then you will converge to a certain number. So that certain number is called the probability. So this is actually the second definition called frequentist definition of probability. So what we are most interested in is to generate the random variates. So we will be talking a lot about the random variables and how to generate them, because in simulations you need to generate data. You need to generate sensible data in order to get the output of what actually you want, and to see what would happen in the stochastic simulation. It start with the good old same sets and functions. What are a set? A set is a collection of objects. The objects are called elements of a set. If S is a set and X is its element, then we can write that X belongs to X, or X is a member of S. The set consisting of element X, Y, and Z is denoted by S equal to X, Y, Z. There is no particular significance given to the order or arrangement of the elements of the set. Elements of the set are not order pairs, so there is no order in that. You can write X, Y, Z, you can write Z, X, Y, whatever you want. Thus, the set X can also be represented like that. A set having no elements is called a null set, and it is denoted by phi. So this is a very simple thing. I'm just reading it. What the characteristic of a set? A set is said to be countable if the elements of the set can be put into a one-to-one correspondence with positive integers. The most basic concept of counting comes from a shepherd from very old time. When he take his sheeps out, he always take one pebble from box on the left hand side, and then he put pebble on the box to the right hand side. And when the sheep returned home at the evening, he did the opposite, taking the pebbles from the right hand side box and then putting them again into the left hand side. So if the pebbles are equal to the number of sheep that actually entered again into his barn or yard, so he was happy. If pebbles are more and sheep are less, he actually searched for the number of sheep that didn't return, and if pebbles are less and sheep are more, he became very happy. So these type of counting techniques are one-to-one correspondence. Say, for example, you all are sitting in your houses, and you can see if you look at your computer screen or laptop screen, and if you look into your room, you can find three or four objects. You can always count them. So in your mind, you have a number line of natural numbers, and you associate each object to that number actually to that line. So okay, I'm sitting in my bedroom, and I have my cloth hanger in front of me. I have my a fan in front of me. I have a bulb in front of me. So I have three objects. How I say that they are three? So actually there is a natural number line in my head that counts the cloth hanger as number one, the fan as number two, and the tube light or the bulb as number three. So there is a one-to-one correspondence between the objects you are seeing, you are experiencing, and a number line which is actually built in your head. So that's why we that's how we do counting. So a set is called finite if it is empty, or if it is element that can be counted with the counting process. A set which is not countable is called infinite. There is another debate, but I'm not going through that. If every element of set A is also a member of set B, then A is said to be contained in B, and A is called a subset of B, denoted by A, that subset symbol. So the concept of subset and superset is over there. Two sets are said to be disjoint if they don't have any common element, or in other words, if the intersection is a null set. The largest of all is called a universal set. So all of the sets could be thought of as elements or subsets or parts of those of that big set is called universal set. If all of the elements are of two sets are equal, they are equal if exactly the same elements, otherwise they are not equal at all. So set A has can have four elements, set B can have four elements, but the elements could be different. So it doesn't mean that the count of four would actually set them equal. Second concept is a function. A function is a mathematical construct consisting of three components. So we have domain X, we have codomain Y, and we have a rule that assigns between X and Y. So if I say Y equal to X square, so in that case, what I'm saying is every element of Y can be represented as an element of X being squared. So if you take an element of X, multiply it by itself, you can get element of Y. So the rule is or F, which is saying is the rule of corresponding is saying that make it square, make it multiply by itself. So this is F in that case. So for any element of X and for any element of Y, this is the association that if you take any element of X and if you multiply it by it yourself, you will get one element of set Y. So this is a function. For X belonging to X and Y belonging to Y, a function is rule defined by. So basically that arrow is actually the rule. Uh, Y equal to 10x, what it is saying, for any element in the set X multiplied by 10, you will get the corresponding element in set Y. Y equal to 5x says that for any element in set X multiplied by 5, you will get the corresponding element in set Y. Y equal to 2x, Y equal to x plus 4. Y equal to x plus 4 said that take any element of X, add 4 to it, you will get the corresponding element of Y. So this is the rule, or a function is called a rule that sets an association, that sets a relation between the member of set X and member of set Y. If two functions are equal, so if they have same domain set, the same condition codomain set, and the same rule of correspondence, so they would be equal. What are the characteristics of functions? The range of a function f is a set of elements in the codomain Y that are associated with some elements of the domain X under rule of correspondence. If the codomain of a function and the range of the function are equal, then the functions are on to. So codomain and range are slightly different. I'm not going into that detail right now. Uh, If element of the domain maps into unique element of codomain, their function is to be one to one. There are three types of function: one to one function, on to function, and one and on to function. So there are three types of function. So this is actually talking about that. A function that has an inverse. If a function is on to one and on to, then it can only have an inverse. Otherwise, a function can't have an inverse. So if function is one to one and on to and the inverse, then it's for all x. So for example, let's talk about five numbers in domain x. Say 1, 2, 3, 4, 5, and I don't know the numbers of domain of codomain or range y, because I didn't set a set of correspondings. I say it is 10 times of x. So the set of corresponding would be y equal to 10x. So if I have five numbers 1, 2, 3, 4, 5 in x, I would have five corresponding numbers 10, 20, 30, 40, 50 in set y. So the rule of correspondence is set take any element of x in the x set, multiply it by 10, and you will get the corresponding element in the y set. So this is actually the rule of correspondence. So is this function invertible? Yes, this function is invertible because it's 1 1. Why it is 1 to 1? Because every element of x is assigned to a unique element of y. So 1 is assigned to 10, 2 is assigned to 20, 3 is assigned to 30, 4 is assigned to 40, and 5 is assigned to 50. Okay. Is there any element of the domain left? No. Is there any element of the range left? No. Then it is on to. So elements of domain should be there, should always be used if it is a function. But the element of range, if all of the elements of range are being used, there is nothing else in the range. So we only have five elements: 10, 20, 30, 40, 50. So this function is invertible. So we can always take an inverse. So what would be the inverse? So if y equal to 10x, then x would be equal to y upon 10. So for every element of y, if I divide it by 10, I will get the corresponding element of x. So this is the concept of 1 1.